All right. Vertical and horizontal particle motion. Again, the tie-in with optimization is not much. It's just that in the process of working these problems, somewhere you usually set a derivative equal to 0. That's the connection to optimization. So there's not, again, that's a loose tie to what we've been doing. You also see that there's not a whole lot of notes to take. There's a whole lot of notes there. So definitely pay attention, highlight, star, whatever you think is important. I'll note some things as we go. But there's not a whole lot on this page. When we turn the page, we'll have a problem to work. In general, t is time, but in theory, t could be any other variable. So pay careful attention to each problem's t restrictions. And by that we mean if t represents time, can t be negative? Be careful, maybe, depending on like when you start your clock on the experiment or in the problem. Like maybe something happened 3 seconds ago or 10 seconds ago. So maybe, I don't know that I give it a strong yes. I would say maybe, but not usually. But it can happen. If t equals 0 represents noon, what value of t would represent the time 2 hours before noon? So what would t be at 10 a.m. if t equals 0 is at noon? -2. You're going back in time. And like you can't physically go back in time, but like 2 hours before now was t equals -2. Number 2, S of t is frequently used for the position, but other variables can be used. Of course, x of t is often used for horizontal motion, y of t is often used for vertical motion. I think in physics, a lot of times we use x and y. A lot of times in here, it won't be two-dimensional problems, it'll be one-dimensional problems, and sometimes we'll use s, sometimes x, sometimes y. So it doesn't matter, any of those. Here's where things get important. V of t is s prime of t. So the velocity is the derivative of the position. Velocity is derivative of position. Maybe we should put that in words as well. Velocity is derivative of position. In physics, you don't use the word derivative, but you do talk about the slope of a position graph is velocity, change in position over change in time. Think about units, meters over seconds. So maybe there's a connection there between position and time, or position and velocity. Acceleration is the derivative of velocity, which means it's the second derivative of position. Acceleration equals dv dt. So acceleration is derivative of velocity. Change in velocity over change in time. In fact, in physics, I should have done this on the previous one, like v2 minus v1 over t, like that was one of those motion equations in physics. But that's like, that equation would be like an algebra slope, so that's an average acceleration. We're going to do instantaneous acceleration, so dv dt. So one of those is an algebra problem, and one of those is a calculus problem. It's the old average rate of change versus instantaneous rate of change. I'm tying that in there because I think you're familiar with the average rate of change equations. You did that a bunch in physics. Okay, here's another physics thing. Speed is the absolute value of velocity. Speed of the particle at time t is the absolute value of the velocity at time t. So speed can't be negative. Speed is always positive. Here's some more physics things. The particle is at rest when the velocity is 0. right? You remember from physics the problem would say a particle starts from rest, and that's like code word for v equals 0. So v equals 0, that's the same thing as rest, or at rest. The particle moves to the right or up when velocity is positive. Right or up. I think that makes sense. That's usually what we think of as positive, is going to the right or moving up. The particle is moving left or down when the velocity is negative. The displacement, another physics word, the displacement of the particle on that time interval is the value of your ending position minus the starting position. So displacement is just where you stopped minus where you started. So displacement can be negative. When we get to integrals, we're not there yet. It's the opposite of a derivative. The displacement will be the antiderivative of velocity, which I don't know, maybe makes sense. To get from position to velocity, you take a derivative. So to get from velocity to position, you take an antiderivative. Perfect. SVA. You take derivatives to go that way. That's all we know how to do right now. Later on, we'll take antiderivatives to go the other way. But for us, for now, you take a derivative to get from position to velocity, from velocity to acceleration. After we learn about antiderivatives, we revisit motion, and we throw in some antiderivatives where we go backwards. Right, the total distance traveled, number 6. You find the sum of the total distances to the right and the total distances to the left, and you figure out like how many, how far did you travel. Distance is always positive, so we'll use absolute values. When we get to integrals, again, you don't have to worry about this yet, but this integral versus that integral, I guess we may as well show it. You'll see it later when we are doing integrals. If we put absolute value on there, we'll get distance. If we don't put absolute value on there, we get displacement. Classic example from physics. If you go 4 times around the track, I guess we'll go in you've got a distance and a displacement. Right, track people. So how far have you run if you go 4 times around the track? What's the total distance you traveled? What is it? Yes, but what is it in meters? Make it easier. 1,600? 400 meters around. So you run around 4 times, you go 1,600 meters, you win a mile. Good job. What's your total displacement if you start here, run around once, twice, 3, 4 times? You know what your total displacement is? 0. So be careful with distance versus displacement. Displacement is just where you started minus where you finished. So if you didn't really go anywhere, your displacement is 0, even though you ran a mile. So be careful about distance and displacement. Related words, but definitely not the same word. And it's usually better if in a problem we ask for both, because then you'll recognize that, wait a minute, that's 2 separate things, I better be careful. The trouble happens if we only ask for one and people give the other one. To find when the speed is increasing or decreasing, we need to know where speed prime is positive or negative. Right? That makes sense. If the derivative of something is positive, that means you're increasing. If the derivative, I should go the other way. You're increasing. If the derivative is negative, you're decreasing. But speed would be the derivative of the absolute value, and taking derivative of absolute value is complicated. So we don't really want to do it this way, because that would be a pain. There's a shortcut. You definitely have to know this. Shows up on the AP test, frequently in the free response questions even. Particle is speeding up when velocity and acceleration have the same signs. They're working together, so you're going faster. The particle is slowing down when velocity and acceleration have different signs. Let's think about this. So let's go with the easiest case first. If you're, I'm going to make it like a table here. See if this works. See if we can think about what goes in the boxes here. So, if velocity is positive, that means you are moving, whoops, that should be positive and negative. So you're moving forward if your velocity is positive. I don't even know what I'm going to put in those boxes now that I think about it. If you're moving forward, the velocity is positive. Oh, now I know what I'm doing. If you're accelerating, so you hit the accelerator, you go faster forward, right? Like, think about driving. You're speeding up. That's the easiest box to fill in. Driving down the highway, you need to pass somebody, you press on the accelerator, you go faster, your acceleration is positive, your velocity is positive, you're speeding up. Let's say you're moving forward and you push the brake. So you're moving forward, but you're slowing down. Your velocity is decreasing. That column, kind of an easy column. That's the column you're used to. The other column is where things are hard because you're moving backwards. So you're backing out of your driveway. Very carefully so you don't hit the mailbox, right? Very carefully backing out. Somebody hit the mailbox? Two of you looked at each other and smiled. No one wants to confess? Okay. I mean, a common early driver mistake, right? It's hard backing down a driveway, especially if your driveway's curved. It's really tricky. So you're moving backwards down the driveway. Your velocity is negative. You're going backwards. If you press the brake, you slow down, right? So you press the brake, you slow down. But when you press the brake, this is the weird part, your velocity is changing from -5 to -4 to -3 to -2 to -1 to 0. So your acceleration is positive. So you're slowing down. You know you hit the brake to slow down. That part's not confusing. What's confusing is when you hit the brake and you're going backwards, your acceleration is positive. That's the weird thing. Does that make sense? Say it if not. Okay, a few of you are honest and be like, what are you talking about? I'm pressing the brake and my acceleration is positive. So let's say you're in reverse and your speed goes from -10, so that's pretty quick to be backing out of the driveway, -10 miles per hour to 5 miles per hour, or to -5 miles per hour. So you're slowing down. And let's say that happens in 1 second. We'll use some physics here. V final minus V initial over time. Your final was -5. Your initial was -10 in 1 second. So not worried about units, but your acceleration would be positive because your velocity is changing in the positive direction. You're headed toward the positive direction because you were going really negative and now you're going less negative, so your acceleration is positive. That's weird.
So are you saying that velocity is like the way you're moving, like the direction?
Yes, definitely. The sign of velocity tells you which way you're going. Yes. Right? If you're in reverse, you're going negative 10 miles an hour. Or negative 5 miles an hour, however fast you're going. Well, your velocity is that. Your speed is still just 5 or 10, because speed is always positive. Right? It's why the thing in the car is a speedometer, not a velocityometer. That would be weird if the arrow went into the negatives, because you would back it up. Your brain doesn't think like that. If you're going backwards and you press on the gas, you know you're speeding up, but your acceleration is negative because you're going faster in the negative direction. If you go from negative 5 to negative 10, your acceleration is negative, but you're speeding up because you're going backwards. It's hard to think about. The easier way to think of it is if velocity and acceleration are working together, then you're speeding up. If velocity and acceleration are fighting each other, then you're slowing down. So this is a spot where you don't really have to understand all of it to get it right. Velocity and acceleration have the same sign, working together, you're speeding up. Maybe speeding up forward, maybe speeding up backwards, but speeding up. Let's do an example here. Position of a particle that is moving in a horizontal line is given by this equation: S of t equals t cubed minus 6t squared plus 9t. Where t is in seconds, t has to be greater than 0, so no going back in time on this problem. Find the velocity of the particle at time t. So find the velocity. So you look back at the previous page, you're like, wait a minute, what was velocity? Well, velocity is the derivative of position. So we have to say v equals ds dt. And some of you won't like this, but you really won't like it when I take off for it. That's why I'm warning you now. You have to show that v is ds dt. You have to make that statement. I know it's easy, and most of you could jump right past it and just give the velocity, because taking that derivative isn't hard, but you have to say where the velocity came from. You have to say that v is ds dt. I guess the flip side of having to show that is there are points associated with that. So if we get to one where the velocity is weird or crazy or complicated, and you aren't sure how to take a derivative, you will get partial credit by at least communicating that you know that velocity is derivative of position. And then you'll get the rest of the points by accurately taking the derivative of position, which I bet Tristan can do for us. What's the derivative of t cubed minus 6t squared plus 9t?
3t squared minus 6t plus 9.
Think about that middle term again. There you go, minus 12t plus 9. You said plus 9, and I wrote the wrong thing. So we take a derivative of position to get velocity. And again, that's an easy one, but you have to show that v is ds dt. Part B. What is the velocity at exactly 2 seconds? What is the velocity at 4 seconds? Lexi, what do you think we should do to figure out the velocity at 2 seconds? You're like 2/3 of the way there. Plug in 2 for t, where?
In the derivative equation.
Perfect. Plug in 2 for t in the velocity equation because we're looking for velocity. I mean, I hope it sounded obvious when Lexi said it, but sometimes people get confused. They're like, oh, plug in 2 for t, but they plug it into position. We want velocity at 2 seconds. So velocity at 2 seconds means plug 2 in for t. And that's a safe stop, so I guess you could leave it like that. 12 minus 24 is negative 12, plus 9 is negative 3.
Do you have to give the
Units? Is that the word you're looking for? I was just thinking about that, and I'm looking. It didn't ask for them, so no. But let's do, just to make sure, velocity. I mean, you probably know what velocity is, but even if you weren't sure of the units, ds over dt would help you know the units. S is in meters, time is in seconds, so velocity is in meters per second. Velocity at 4 seconds, not the same answer, but the same process. Plug 4 in for t. So what is that? 16 times 3 is 48. 48 minus 48 goes away. Plus 9 is 9. So V of 4 equals 9 meters per second. Find the acceleration at time t and at 4 seconds. Well, I know we just did this, so maybe this is cruel, but what the heck? Marie can do it. How do I find the acceleration? So, I don't want the answer yet, just how do I find the acceleration? Yep, you're right, you're looking in the right spot. It is another equation, but how do I get that equation? Be careful how you phrase that. You take the derivative of what? Of velocity, which is the second derivative of position. But when you aren't specific and you just say find a derivative, it's like, well, derivative of what? So dv dt will tell us the acceleration. So Maddie, we found v up here. What is dv dt then? 6t minus 12. So, Will, if I want to find the acceleration at 4 seconds, put 4 in for t. Again, that's a safe stop, but it's also easy enough to do 24 minus 12 is 12. Ooh, units? Anyone remember their physics? Or you can figure it out from dv dt to get the units of acceleration. How many of y'all took physics last year or this year? Okay, most of you. So what's the units for acceleration? Meters per second squared. And so you can go with meters per second squared. If for some reason you forgot meters per second squared and you were just going by like this formula and you're like, well, I don't know what it is, but it's got to be velocity over time, you can leave that as an answer. That's an okay answer. I mean, most people don't leave it like that. That's the same thing as meters per second squared. But it comes from meters per second because it's a change in velocity over time. So we abbreviate that and we forget where it comes from, and then it gets confusing. It's like, why is there 2 seconds down there? Well, it's change in velocity over change in time. Avery, when is the particle at rest? What does at rest mean?
0.
What is 0? V. Think about driving your car. You're not moving anywhere when velocity is 0. So there's our justify, is rest means v equals 0. So I'll set velocity equal to 0. That's, I guess, annoying, but not too bad. Factor out a 3. Factor out what's left. So t equals 1 and t equals 3. I didn't say indicate units, but seconds. So 1 second and at 3 seconds, velocity is 0, which means we're at rest. Part E, when is the particle moving to the right? When is it moving to the left? Justify your answer. So moving to the right versus moving to the left. Claire, how do I, what's going to help me figure that out? I don't need an answer right now, but moving to the right, moving to the left. That's speeding up and slowing down.
Okay.
So that's in your brain. It's good it's in your brain. Look at number 4.
Oh, when it's positive or negative.
When it's positive or negative. Sort of gets back to Sophia's question earlier about the sign of the velocity tells you which way you're going. The sign of the velocity tells you which way you're going. So moving to the right means V is positive. Moving to the left, that would be where V is negative. These two questions kind of go together because we already found our 0 velocities. So if we've got where it's 0 and we want to know where it's positive or negative, what kind of thing have we done before when we know the zeros and we're looking for positives and negatives? The sign chart. So let's do a sign chart with 1 and 3. So I think we could check 0 and 2 and 4. When I say check them, where should we be checking them into? Now we got a position equation and we got a velocity equation. Where am I plugging 0, 2, and 4 in? Velocity, because I want to know the direction that things are going. So V of 0. Where did my V equation go? I'll rewrite it right here. 3t squared minus 12t plus 9. So V of 0, that's super easy. That's 9. So V is positive when we're less than 1. V of 2. Free response questions on the AP test frequently do this. You're like, oh man, now I got to go find out what V of 2 is. Anybody know what V of 2 is already? We did that already. A lot of times on AP test, they'll ask you for some things. You're like, oh, that's just kind of some random value they asked for. And then later on, you're like, oh, now I know why they asked me for that. V of 2 is negative 3. So V is negative. V of 4. Oh, they asked me for that. I did that one already as well. That was 9. So that's positive. Okay, so we're moving right. We need to answer our question fully, completely, and justified. Moving right on 0 to 1 and 3 to infinity because now we've kind of already answered this, but we want to put it in our final answer statement to make sure that the grader, me, sees it and knows what you're talking about. How do I know that we're moving right from 0 to 1 and 3 to infinity? Velocity is positive. And then we're moving left from 1 to 3 because, Emma, what's my reason for knowing that we're moving to the left? Velocity is negative. So make sure you include that as in your answer, as part of your answer, to get the justify part. Draw a diagram to represent the motion of the particle. Don't know that we do this in physics, which is maybe why people struggle with it. Like everything up till now, had at least some connection to physics. You're kind of familiar with the stuff. I don't know that we do motion diagrams in physics. So motion diagram is, we're going to plot the position. Cody? Why didn't I start with negative infinity? Anybody know the answer to that question? It's all the way at the top of the page. So you're right, velocity is positive at, like in the equation, at negative 1, 2, 3, all the way out to negative infinity. But why did I not include negative infinity? Because it told me to start at 0. So starting at 0, we'll start at 0. You would not lose many points if you put negative infinity there, right? Because you'd have done everything right. You'd just ignored a condition at the beginning. Okay. Draw a diagram to represent the motion of the particle. Your diagram will plot the position. Will include t equals 0 and the times when v equals 0. So I need a kind of a table of values to start with. And this should kind of look familiar. I want to include my zeros, or excuse me, not my zeros. I want to include my endpoints and my critical points. Critical points are where the derivative is 0. So that was at 1 and 3. We already found some of this information here. So I'm making a table that includes the endpoints. We're not going to worry about infinity. We'll worry about that in a minute. Starting point, ending point, and the critical points. So we've done that before. It's called the candidates test when we were looking for absolute max and mins. It's not called that here, but we're doing the same thing. So I'm going to plug in 0 and 1 and 3 to kind of get me started here. S was t cubed minus 6t squared plus 9t. So S of 0 is 0. That's the easy one. S of 1, 1 cubed minus 6 plus 9. That would be 4. S of 3 is going to be a little more complicated. 27 minus 6 times 9 is 54. Plus 9 times 3 is 27. Well, I thought it was going to be more complicated. But it's at 0. So we're going to start at 0, 0. We're plotting position. So at position 0, right, this is a kind of a number line graph of S because we're plotting the position. Plotting the position. And we don't have another axis. This is maybe what's weird. So we're just gonna label it. Say there's t equals 0. We're starting there. 1 second later, we're at position 4. 1, 2, 3, 4. So we move to position 4 at t equals 1. So I'm plotting all my points, but I'm plotting them in a weird way that we've not done before. I'm plotting them on a number line rather than like an XY graph. At t equals 3, we're back at 0. So we move back at t equals 0, or t equals position 0 when time is 3. And then, which way do I go after that? Like, I didn't put any more points down here. But which way are we moving after 3? Look back at that. Moving to the right from 3 to infinity. So we take off that way. So that's the motion diagram. Great. Yeah. So you plot position, use endpoints and critical points. So you were used to making tables with endpoints and critical points. Draw a diagram to represent the motion of the particle. So you finish and you get a picture of what the particle did. It started at 0, it moved to the right 4, then it moved backwards back to 0, and then it took off from there. That will now allow me to answer the next question. Find the displacement. Whoops, I don't need to answer displacement. Because displacement during the first 5 seconds is just s of 5 minus s of 0. I don't need a motion diagram. I don't need to know how we got there. I just need to know where we are at 5 and where we are at 0. So where we are at 0, I already know that. But I need to now find s of 5. So 5 cubed minus 6 times 25 plus 9 times 5. 125 minus 150 plus 45. And you could safe stop some of this stuff, so you could just leave that as s of 5 and just plug in what we know. But I want to get an answer, so I'm going to plug in my pieces here. Negative 25 plus 45 is 20. So 20 minus 0 is 20. So the displacement during the first 5 seconds is 20 meters. Can't probably phrase this. We're 20 meters away from where we started. That's what that means. 20 meters away from where we started. The next question is, find the total distance traveled by the particle during the first 5 seconds. Well, now we're going to have to be careful. We're going to add, I don't know how to phrase this, the left travels and the right travels. Right, the leftward distances and the rightward distances. Add the pieces or the trips, however you want to phrase this. Let's look at our motion diagram. We already have s of 5. That was out there at 20, so somewhere way out there. There's 20. The graph, not the scale, right? So let's look at the pieces. There's a 0 to 1 piece. There's a 1 to 3 piece. And I guess these are times, I should say. So 0 to 1. How far did we travel? What's the distance we traveled during that first 4 seconds? Or first 1 second? 4. I gave away the answer there. So 4 meters. Alright, from 1 to 3. Direction doesn't matter, just how far did we go from time equals 1 to time equals 3. Also 4. And then how far did we go from time equals 3 to time equals 5? That was 20. So we add up the 4 and the 4 and the 20, and we traveled 28 meters. The actual, the odometer on the car would be 28 meters. The feeling in your legs would be, I ran 28 meters, even though your displacement was only 20. Sorry, doing attendance here before I get the phone call. And I'm recording. Oh well. Okay, so the difference between displacement versus total distance. Displacement is just where you landed minus where you started. Distance is more complicated. You usually need a motion diagram to like add up the pieces. Well, how far did I go right? How far did I go left? Back and forth. And you really need a picture to help keep track of things. All right, speeding up and slowing down. Claire, how do I know when I'm speeding up and when I'm slowing down?
Velocity's positive or negative.
Be careful. You answered the right question earlier. It's not velocity positive or negative. You gave this answer earlier to a different question.
Oh, different signs. Same signs.
Same signs or different signs of what?
Of velocity and acceleration.
So speeding up, A and V have same sign. Slowing down means A and V have opposite signs. Okay, I already have a sign chart for velocity, so I'm just going to replicate it down here. So we already did that. I don't really need to do it again, but since I'm looking for where their signs are the same or opposite, I would like to put the acceleration sign chart right underneath it, and then it's really easy to line up. Oh, they have the same sign, they have the opposite sign. So let's do that same process we did for velocity. Now let's do it for acceleration. So I hope you like taking derivatives and setting them equal to 0, because we're going to do that a lot. So it's e equals 2. That's my critical point when the derivative is 0. Let's check 0 and 3. When I say check them, where am I checking 0 and 3 into? A or V or S? Got more options now. If I want to know the signs of A, then I need to check it into A. So A of 0 is negative 12. That's negative. A of 3 is 18 minus 12. That's positive. And I like my stacked number lines because then it's just really easy to see where their signs are different. So positive, negative. There's negative, positive. So it's slowing down from 0 to 1 and 2 to 3. Because A and V have different signs. And it's speeding up. Let's see when they match. It looks like 1 to 2 and 3 and on. 1, 2. 3 to infinity, we're speeding up. Because A and V have the same sign. Obviously, we're going to stop there. Maybe not obviously. Let me give you the worksheet for today, the worksheet for the rest of the unit even.